Imagine the last ocean on Earth. It does not end with a wave. There is no giant drain and no wall of steam flying intact into space. The final water molecule rises alone, is broken apart by ultraviolet light, and loses its lightest atom to the dark. Earth does not lose an ocean as water. It loses one hydrogen atom at a time. That distinction is the entire investigation. Oceans are heavy, gravity is strong, and ordinary water vapor cannot simply climb out of the atmosphere. To erase the seas, Earth must first move water past a hidden atmospheric barrier, then split the molecule, then accelerate hydrogen beyond escape. Each step is a bottleneck. Modern Earth is protected because the first bottleneck works extraordinarily well. Most weather lives in the troposphere. Rising air cools until water condenses into clouds, rain, or ice. Near the tropopause, roughly around the altitude where passenger jets stop climbing, temperatures become extremely cold. Air entering the stratosphere is freeze-dried. NASA studies call this region the tropical tropopause layer. It is a cold trap, a narrow gate that returns most water to the world below. That means the coldest part of the atmosphere helps preserve a warm ocean. The stratosphere above contains only tiny amounts of water compared with the lower atmosphere. Water that never reaches the upper atmosphere cannot be efficiently destroyed by ultraviolet radiation. The ocean survives not because every molecule is gravitationally imprisoned, but because atmospheric circulation keeps most molecules away from the exit. Suppose Earth warms until that gate begins to fail. More water evaporates, and warmer air can hold more vapor. If enough water enters the stratosphere, ultraviolet photons split H2O into hydrogen-bearing fragments and oxygen. Hydrogen is the lightest element. In the thin upper atmosphere, collisions, thermal motion, solar radiation, and charged particle processes can give some hydrogen enough energy to escape Earth's gravity. This is called a moist greenhouse, but it is not identical to a runaway greenhouse. In a moist greenhouse, the surface may still contain liquid water while the upper atmosphere becomes wet enough for long-term hydrogen escape. A runaway greenhouse is the more extreme state in which absorbed sunlight overwhelms the planet's ability to cool by infrared radiation, driving wholesale ocean evaporation. Different models place these thresholds at different temperatures and solar fluxes. James Casting's 1988 Icarus calculations made the mechanism famous. Water-rich upper atmospheres can feed photolysis and hydrogen loss. Later three-dimensional models complicated the boundary. Colin Goldblatt, Ravi Kaparapu, Eric Wolf, and others showed that clouds, circulation, humidity assumptions, and atmospheric composition can delay or reshape the transition. There is no honest countdown accurate to a single year. There is a physical sequence with uncertain thresholds. The sun supplies the slow pressure. As a main sequence star ages, helium accumulates in its core, the core contracts, and fusion proceeds at a higher temperature. Solar luminosity gradually rises. Long before the sun becomes a red giant, extra sunlight can push future Earth toward climates in which the cold trap weakens. Depending on model assumptions, ocean loss becomes a concern on roughly billion-year timescales, not next century. This must not be confused with modern climate change. Human-caused warming is dangerous on human timescales through heat, sea level rise, ecosystems, food, and extreme events. But today's atmosphere remains far from a sun-driven moist greenhouse ocean escape. Saying the oceans will not leak to space this century does not make present warming harmless. It means two different mechanisms should not be collapsed into one dramatic sentence. Once hydrogen escapes, what happens to the oxygen? Splitting water leaves it behind. Some oxygen can also escape, especially under intense high-energy radiation. Some reacts with volcanic gases or oxidizes the crust and mantle. If the sinks cannot keep up, oxygen could accumulate without life. This is why astronomers treat oxygen on an exoplanet carefully. Under some histories, a dead world can manufacture an oxygen-rich atmosphere by losing water. Venus is the warning written next door, although its exact early history remains debated. Its atmosphere contains far more deuterium relative to ordinary hydrogen than Earth's ocean. Deuterium is heavy hydrogen. Lighter hydrogen escapes more easily, so the residue becomes enriched in deuterium. A 2024 Nature study identified an additional present-day Venus escape pathway involving HCO plus chemistry, helping explain how the planet could finish losing water. The isotope ratio is not a photograph of an ancient ocean. Scientists must estimate starting composition, volcanic resupply, atmospheric chemistry, and multiple escape channels. Yet the basic logic is powerful. When a planet preferentially loses light hydrogen, heavy hydrogen remains as a chemical fingerprint. A dry sky can preserve evidence that water once passed through it. Mars shows another version. NASA's MAVEN mission found that solar wind and radiation drove major atmospheric loss, while high-altitude water and dust storms can deliver hydrogen to escape routes. Mars is smaller, colder, and less gravitationally binding than Earth. It did not need to repeat Venus exactly. 3 neighboring rocky planets demonstrate that retaining water depends on size, atmosphere, star, magnetic environment, and time. Now accelerate the thought experiment. If extra heating abruptly loads the stratosphere with water, the sky becomes a chemical factory. Ultraviolet light breaks molecules above the weather. Hydrogen leaks upward, oxygen reacts below. Sea level falls slowly compared with human disasters, but relentlessly on geological clocks. Salinity rises. Coastlines retreat. Carbon cycling changes as weathering and biology lose their liquid engine. The last habitats would not be open beaches. Water could persist in deep basins, shaded caves, subsurface pores, polar refuges, or minerals that lock hydrogen into crystal structures. Life would retreat with it. A planet can lose its visible ocean while retaining significant water inside rock. Dry Earth is not a single inventory number. It is a transfer from mobile surface water into space and hidden reservoirs. Could technology stop the process? On billion-year horizons, hypothetical descendants might shade Earth, move its orbit, alter atmospheric composition, or store water underground. Each proposal is engineering far beyond present civilization, and each would need continuous control of an entire planet's energy balance. The scientifically useful point is smaller. Habitability is maintained by active feedbacks, not guaranteed by Earth's address. For exoplanets, the mechanism changes what a telescope should seek. A world near the inner edge of its habitable zone may still show water vapor while already losing hydrogen. Escaping hydrogen, unusual deuterium, or abiotic oxygen can reveal a climate in transition. The habitable zone is not a painted green circle. It is a set of atmospheric processes that evolve with the star. If Earth lost its oceans to space, the final act would be almost invisible. No cosmic suction, only a cold trap failing. ultraviolet photons separating atoms, and hydrogen crossing a boundary it cannot return from. The ocean's greatest shield is not the ground beneath it. It is a thin, cold layer high above every storm. The paradox is precise. Earth keeps its seas because part of the sky is cold enough to make water fall. Next, what if Earth's atmosphere became twice as thick?